arriver. Tu prends moi. Ouais, tu me dis si jamais tu veux des.
J'ai vite de vous demander, ça m'a fait un peu de bruit, je crois de déranger les gens. Est-ce que
Ouais.
vous avez entendu les...
Non, pas du tout. Ça s'entendait pas du tout.
Ça devait être juste
Non. Donc en vrai, tu peux vraiment y aller. N'hésite pas. C'est pas.
j'ai vu que je crois tout le monde là, je sais pas.
Ouais. Ouais, non, vraiment, n'hésite pas. Tu peux y aller. Ça s'entend pas. De toute façon, ouais.
J'avais peur de déranger.
Non, non, t'en fais pas. Tu dérangeras pas.
On lui demande d'écrire un nouveau code et ensuite d'enregistrer sur la dashboard.
Invite you to join.
Ça marche.
Ouais, ça a pas attendre.
All right. Il est passé où tout?
Merde, c'est pareil.
C'est pareil. So I hope you had a nice coffee break. So I'm going just to start the two next sessions. I'm just looking for the next speaker. Oh, sorry, you're there. So for the next session, so we are welcoming Toon Calders, who will talk about unfair usage. Explain yourself. So Toon.
All right, so title of my talk, Unfair You Say, Explain Yourself. So I'm going to talk a bit about explanations in the context of fairness and how we can use them and why they are necessary. However, a large part of the talk will actually be about motivation. Why do we actually need explanations and human involvement? And one of the main statements that I will make is that a fully technological solution is not possible. I will show some examples of some theory we developed to support that. Here I'm preaching a bit in front of the choir. So if we have biased data, we learn models on biased data, then our models may be biased in the end. Just to give one example where this happened, this is in a healthcare risk algorithm that was trained in the United States, and where the insurance companies wanted to predict whether someone would be in need of medical assistance, serious medical assistance in the future. And in order to make this prediction, one big issue was labels. When do we say when someone is healthy or not healthy? And so in order to make this labeling of their data set, they actually used the medical costs that the patient had. And this makes sense, of course. If I spend in the next 5 years 100,000 euros on my health, then probably I'm less healthy right now than someone who will spend 100 euros on health. However, as you can already in the United States, because of socioeconomical situation, black individuals tended to spend less on their health than white individuals, even when they were in the same medical conditions. And as a result, there was actually a large difference in the predictions that the model was making. For black individuals, for those that were predicted to be at peril and maybe need some more assistance in the future, actually there was almost a quarter of them more that were in this situation. And so if you take a white person to be at high risk, a black person to be at high risk, and a black person was at a much higher risk. And this was, of course, because this difference in expenditure for health. And so the old way, the way we studied for many years when we started the research, I think almost 20 years ago, we were thinking about, okay, we have our observed data. In our observed data, we observe something we think is not right. We look, for instance, at demographic parity. Like Arthur already explained, this has to do with, we detect a disparity. For instance, there are more positive labels among males than among females, and we think this is not right, because we have this assumption, let's say it's for jobs, and we have candidates, males and females, it's for ICT job, and in our data, more males are hired than females, but we have this assumption that males and females, if they had the same education, they're equally qualified for the job. So there is something wrong with our data, and if we learn a model directly on it, it will use the gender in order to make the predictions more accurate, or it will use proxies of gender in order to make predictions more accurate. Not to discriminate, but because it's aimed to make predictions more accurate. So that's why we introduced in our learning procedure techniques to make the model fair by design. And many of those techniques have now been introduced in packages, like IBM has this Fairness 360, in which a lot of these techniques have been introduced. Some of the techniques try to massage the data on beforehand in order to make it, to remove certain correlations that we think are undue, and so the algorithm will not pick it up. Some do it afterwards, they look at the models, the predictions of the models, and then, for instance, recalibrate, like Arthur explained. Or some introduce it as a constraint during the learning procedure. And so basically, under these assumptions, there we have our feasible models, we have our optimal model, and then we have our feasible fair models. So we say, and basically we want to have the feasible fair model that is optimal in the set of feasible fair models, because there is a constraint that we do not consider all models. Not all models are allowed, but only a subset of those models. It's logical that those models will be less accurate. And this is what we called the fairness accuracy trade-off. And by forcing us to be fair, we will be less accurate. And this has been observed in many experiments. It's of course logical. You're imposing something. Your predictions need to deviate from what you see in your data. So if you use your data in order to look at the accuracy of your models, then indeed you see, and so what is shown here is the fairness that we impose, the more strict that we are. So for instance, we see a hiring difference of 20%, and so we can say in our predictions we only want to see 10%, 5%, 0%, and the more you go to the right, the more fair we want to be, or the more equal. And here, this is the accuracy of our model. And so the accuracy of the models goes down if we want it to become more fair. But this is, of course, and this is a flaw that is there in a lot of this previous research, because we're measuring accuracy of our models with respect to our data set, and we already assume that is biased. And we believe that males and females are equally capable of doing the ICT job, but the data says differently, and now we're measuring our accuracy on this data set, which does not satisfy some logical assumptions that we think should hold. And so many people did some other experiments where they actually introduced bias themselves. Then you train the model on the biased data set, and then you measure the accuracy of the model on the unbiased data set. And so this is, of course, in reality, we do not have this situation. So we just get the data. We observe some bias in the data, but we can make some controlled experiments in which we just flip a coin. If it's a male applying and we see the label, it's negative. We flip a coin, and with a certain probability, we change the negative label to a positive label. For females, we do the opposite. So we're actively changing the labels in order to introduce bias. And then you see, if you try to correct your model for the bias, it actually becomes more accurate when we measure it with respect to the original data that does not show any bias. This is, of course, logical, because we introduce a distortion in the data, and we make some assumptions how the original data looks like. Our assumptions are right. So if you learn models that satisfy original assumptions, it's not surprising that they may actually become more accurate. It also has a little bit to do with transfer learning. But of course, one crucial piece of information there is, well, we need to know if a data set is biased, and then in what way it is biased. We need to know what kind of assumptions we can make about it. And I think, and this is a flaw in many of those tools. For a tool, a data set just looks like this. It's just a number of characteristics, and it does not have any interpretation of this. And so this can be, for instance, gender, female, male. Just for the sake of the example, I took binary gender. I do not make any statements about that. We have X, and so these are attributes on which we can base our decision. And then we have Y, the label in our data set. So if we now look at this data set, we see a demographic parity difference. And so if we look at the females, then we see that 3/4 of them have the positive label. And for males, it's fewer of those. It's only 4 out of 7. So there's an 18% difference. Does this mean that there is discrimination in the data set or not? Maybe there is, maybe there isn't. If we look at conditional demographic parity, and there we look at the label, but we say, okay, males and females should be treated equally as long as they are similar and they're comparable. Maybe X is the diploma that they have. If there are more males with an ICT diploma, then of course it's logical that we're hiring more of them. So in this data set, if we condition on this attribute X, and then we will see that our label becomes from gender. So that's a good situation if this is an attribute that makes sense to base our decision on. If this is the hobby of a person, well, then it's not, or the tendency to use more words in a sentence. If we look at language models, they can get the gender of a person out of these implicit cues. What we also see is that in this data set, females are underrepresented. Or maybe it's self-selection bias. Females are more self-aware and they're only applying when they think they have a high chance of being accepted. Then we also see that the distribution of X differs between males and females. And there can be all kinds of reasons for this. And this could, for instance, be maybe it's the number of publications in an academic context and whether or not they became a professor. And then maybe females have longer periods of absence because of giving birth, for instance, and on average have less publications. And it could be all kinds of reasons. And if we don't know how to correct. And that's basically the first main message. And this is one of the reasons why I think this evolution of these tools that have been developed and just applying these tools to build models that are fair by design is maybe not the right way to go, because based on which reason there is that the bias in our data is in our data set, there are different ways that we need to mitigate it. And let's just pick one. I suppose that there is selection bias, and there were only qualified females that applied, and they were more self-selective. If we just ignore the bias, then the model will pick up the correlation between females and being female and being more qualified, and so females may get preferential treatment if in future, for instance, it changes who is applying. If we resample the data set, so we oversample a little bit the females that with the negative label, it could be and that we actually get a more realistic distribution, so that would be a good way. If we do affirmative action, and so we force the algorithm to hire at the same rate, well, then males will get preferential treatment. And because we will be hiring more of them, while in the data set, the reason why more females were hired than males was actually the correct reason. So depending on these three, on the situation, some different actions may be required. And so this is something that we then studied in theory. And so we actually extended our model. And so we make this assumption that there is like an underlying fair world. Then there has been some distortion, and so we have our observed data that is distorted, and then we learn and do a fairness intervention. But instead of trying to optimize accuracy in our observed data, we actually want to optimize it with respect to our imaginary fair world. And so this is modeled by, what do we mean by the world is fair? So here we have some fairness criterion. that needs to be inputted into the model. And this is just for algorithmic reasons, this is just assumptions, and males and females are equally capable. So this is something that we may not observe from the data, but we assume that it holds in the real world. But then there was a process such that our data does not reflect this. Maybe there was some selection bias or label bias. And so we study combinations of those. In order to model the different types of bias that may have been introduced, we studied label bias and selection bias. By label bias, we mean that just the label changes for some of the instances. And the way that labels change is correlated with the gender of a person. Selection bias is that we have in the real world, we have lots of instances, but our sample of our observed data, in the sense that, based on gender and the label, some instances have a higher chance of entering the observed data than others. And then how do we formalize the sources of bias? So that's basically what I said. And then what our fairness criterion that holds in the real world. For this, we use very simple causal models in order to model that. And so here, for instance, we have statistical parity, which reflects that A and Y, so A is our sensitive attribute, the gender of a person, and our label, that they are independent, and we make some kind of assumption that our X and the things we observe, they depend on our label. And so this is like the classical learning assumption. And so we have two different classes, and the classes are generated by different distributions. We learn a distribution, so if we observe a new instance, we can guess from which distribution it comes. And so we have our class influences what we observe. And then, of course, also our sensitive attributes influence what we observe, but the sensitive attribute does not directly observe the label, and vice versa. So that is statistical parity. So we assume that this holds in the underlying word, and this is we are all equal. So this means if we have the same attributes, and then our label should be the same. And so the gender should not give us any additional information over the other attributes that they have of people. Then we had the label bias. And so we have some instances may change, and we have selection bias, so some instances may be removed, and the way this is introduced is depends on the A and Y attributes. Now, this is well, there is quite some mathematics behind it that I want to hide away a little bit. But what is the goal? What do we want to achieve? And now we want to see if there are ways to check these assumptions that we make about what holds in a fair world and what introduced the bias. Maybe if you look at the data, we can tell, well, you're claiming that there was some selection bias and that here males and females are equally qualified, but what we observe in our data is inconsistent with your assumptions. If you could do things like that, that would be very helpful to better specify the assumptions that we have and that need to come from humans, or maybe we can even do it fully automatically. And so here we see, for instance, how probabilities get affected in case of label bias and selection bias. So what we see here on the horizontal axis is what would be the probability of having the positive label if you are in the original fair world, and on the y-axis how it's distorted. And so here we see, for instance, for the privilege group, if we have label bias, the way we introduce it in our data, then you will see a linear relationship where the privilege group will actually start at a higher level. Everyone will have a probability of getting the positive label. Even in the fair world, you had 0 probability. Now it will be slightly more, and it's linear. Here in this case, if we look at selection bias, and that are the kind of results that we want to see, and that the relationships are different. And so if the relationships are different, it means that we need to correct for it in different ways. And so here we see a nonlinear relationship, there actually, if you look at the odds, that will be linear. And the odds, the probability of being in a positive class divided by the probability of being in a negative class. And then for the unprivileged group, of course, we see the opposite effect, and that they actually get in the data a lower probability of getting the positive label than in the original world. Now looking at the data, can we observe it? And there we have some mix of results. Some are positive, some are negative. For instance, if we look at sample bias and statistical parity, this can never be detected. What does it mean? That if we have a data set, every data set could have been generated by a process that shows sampling bias, and in your original world, there is statistical parity. So there is assumptions that are basically uncheckable. For those where I have can be detected, this means that there might be situations in which we can see that our assumptions are wrong. And so if there was label bias, some of the labels are changed, like in our insurance example, whether someone is healthy or unhealthy, that was distorted because of using the proxy and the health expenditure. And then if we assume that there is statistical parity, that both populations are equally healthy, which probably also does not hold in this data set, but that we could detect, and that there could be situations where we see that our data is inconsistent with this combination of assumptions. But, and this is the most important, there are situations where we cannot detect it, and the only thing we can do is just rely on input that humans are giving us in the process. Yeah, so this is, for instance, it used to be an animated slide because of the PDF, but here suppose that this is our data set, then it could always come from another data set, and there is a sample bias that led to this data set, and in the original data set, our statistical parity holds. So now we need, so the message from this is we need human input. Looking at the data alone will never be enough. Then what should we optimize with respect to the bias data? Let's assume that we made some assumptions, and we observe and our data is consistent with our assumptions. Then what should we optimize? Can we really learn models that then are maximally accurate in our original world by only looking at our observed data? And so there is, again, another fallacy that we see with a lot of those algorithms, where they actually introduce the fairness for unfairness. And so we have our original world. We assume, for instance, that gender is independent from our label, but it's not true in our observed data. So there was some distortion. Our observation is that the gender is dependent from the label. And so we will learn now a model for which the gender will be independent from the prediction. And we will learn it on our observed data. For instance, we will change the way that our label is, becomes now independent in our predictions. So there we have this mismatch, because basically we are measuring our fairness requirement on our distorted data, and we're trying to make our models fair with respect to our observed data. And this is indeed what we observe if we do then controlled experiments. So we have here our original world. We assume that gender is independent from the label. Then there was self-selection bias, for instance. And so we have more females with the positive label than males. So you observe that the gender is dependent from the label. The label depends on the gender. They're dependent. If we then use a constraint where we force that the predictions for this data set are equal between males and females, we'll actually get a model that, when applied on the original data set, will discriminate against women. And so, bottom line here is a fully technological solution is impossible because we're unable to unambiguously detect biases. So we have a necessity for human involvement. I see there are some talks that talk about using causal models. I'm very happy about it because I think this is a good way to state assumptions on the ideal world and assumptions on the bias process. And so basically what we need are languages to express these assumptions in a way that can be used by algorithms, and methods to verify consistency of the assumptions and the data that we have. Then let's now take one step back. Let's assume that the right assumptions have been given. So we are working in the correct situation. We have the right assumption about how bias was introduced. And let's now introduce fairness as an optimization problem. Then we're still not out of the woods. Because if we optimize our fairness criterions, this has undesirable side effects. For instance, fair classifiers that will make mistakes on purpose. And let me illustrate this. And so suppose one of the fairness algorithms is looking at the errors that we're making. And so we are looking at how many false positives do we have, people that are in reality negative, but we predict them to be positive. Then we look for both groups if we have two groups. And there we say, okay, we do not want there to be a high disparity. We do not want to be large differences in the errors that we make. And the same with the true positives. If you look at the equal odds criterion, that's basically requiring that the true positive rate and the false positive rate should be the same for both communities. So then we observe, we learn a classifier, and we observe that this is not the case. It makes more errors on black people than on white people, for instance. And then we have this implicit assumption that basically we can make the algorithm a little bit better, the model a little bit better for one community, but this will then go at the expense of the other community. It's like a balance. But this is almost never true. Why is this? Because these sensitive attributes are usually highly correlated with other attributes. If there would have been a way to make the model better and to reduce the errors for the black community, the algorithm would have used these proxy attributes in a decision tree to decide, okay, it's a black person, so I need to use another model, this better model for this. And so since the algorithm did not learn a better model for the black person, and the only way to make the errors equal is basically by introducing errors on purpose on the white people, and make it equal like that. And that's an undesirable side effect. Similarly with calibration. So with calibration there, what we want to have, so suppose that we divide people in risk categories, high risk, low risk, and then we want to have this condition of sufficiency. We want that knowing the label that someone got is sufficient in order to know the real risk level. For instance, we're predicting recidivism, and we're saying high risk means 70% probability that there will be recidivism, and low risk, and that's only 30%. And then basically in the context of fairness, this calibration is then extended to group fairness, where we say that if you look at the risk level in the high risk group, it should be the same for, let's say, black and whites. So it should not be the case that if we look at the high risk, that for a black person, high risk means 60% probability of committing a crime again, and for a white person, it's 80% probability, and they need to be the same. And so basically, when we learn an algorithm, I imagine this as putting instances into buckets based on some characteristics, and each of those buckets has a probability of having the positive label, having the negative label. So if we would just learn an algorithm, we do not have access to the sensitive attribute, let's say. And so we put people in a bucket, and this is the bucket of people with 60% probability. And there is no way of splitting it up, and we cannot identify a subset of those people that have 70% probability. And so this is the best we can do. And there we have a bucket with 40%, and there we have a bucket with 30%. And so this would be a prediction. And so a new instance comes, we look in which bucket are you in the 60% bucket, so I'll predict 60% risk for you. Now, if you look at group calibration, it could be the case that if you look at the buckets that we have, and that in this bucket, if you look at the white people, it's 60%, and for the black people, the risk is 40%. And this could be the case because there might be a lot of other attributes that influence the risk of someone. And let's look at, let me slightly change the example with insurance, car insurance. Males make more accidents than females, and so, but we cannot use the gender, so we have put people into risk categories, into risk buckets, and we look into one bucket, and in that bucket, males have 70% probability of having car accident, and females 50%, so it's not calibrated. And now we're forcing our algorithm, because we're making it an optimization problem, we're forcing the algorithm to make the buckets equal. And what the algorithm will do is it will take some males they have almost no risk of having a car accident, and they will take it out of one bucket and sprinkle it into the other bucket in order to decrease the probability in that bucket. And in the end, you will end up with some kind of fairness gerrymandering, where you will have selected really strange profiles of different people. You will have grouped together people living in Texas and that are 37 or 41 years old and have 2 or 5 children. Because if you look at that specific subsection, then the risk became equal. And so this is treating fairness as an optimization problem is actually problematic in many cases. So this is the first example. And so basically, it's a bit like this kind of solution. We have a dilemma. Our algorithm, it's like solving a trolley dilemma in this way. There is no way to be fair. That's the situation. We can't change or classify it any way that we want. There is no way to be fair. And so we make it fair by just shooting the person that was not negatively affected by our classifier. And this is something that we need to avoid. And this is like where a large part of our research is about. Like what are the boundaries? Like how much can we do? How much can we correct algorithms without getting into this kind of situations, this kind of solutions? Let's skip over this one. And so this is my second intermediate conclusion. I think even if we have all our assumptions right, in order to correct our predictions in the correct way, there is a need for explanation. We need to understand why there are these disparities. And then it's a policy decision, what will we do about it? Like in the hiring example, we are hiring fewer females than males. How are we going to correct for that? There is no automatic way that will be entirely fair. And for instance, we will do some affirmative action in order to break this chain of disadvantaging one gender, for instance. And a first very simple idea, I admit it's extremely simple. What we did is, and this is called the Prekov algorithm, it has been published in Machine Learning Journal, is we just look at counterfactual explanations. And counterfactual explanations, that are explanations like you have an instance and it got a negative label. What is a minimal change that I need to make to that instance in order that it would have gotten the positive label? For instance, if your age would have been higher, you would have gotten the loan. Or if your income would have been 500 euros higher, you would have gotten the loan. Or maybe if you would have been a male instead of a female, you would have gotten the job. And basically what we're looking at is we're looking at counterfactuals, and we're comparing counterfactual between two communities. Again, it can be generalized to more general settings, but again, we consider that our population is divided into two groups, and we look at the counterfactuals and which attributes are used more in one group than in the other group. And so basically, we're looking at the attributes, the number of instances for which the label would change if we change the ith attribute. And we're comparing between the sensitive and the non-sensitive group. And even this simple idea already is very helpful. One data set that is used that has been beaten to death in research, I would say, is the adult data set. 20 years ago, we started using this data set. It's a data set in which you want to predict whether someone has a high income or not. And you see in this data set there is a difference between males and females. So it's the problem setting is a little bit artificial. And then you're saying, when I make predictions, I want to predict at an equal rate. If you then look at explanations, which attributes are more likely to appear in a counterfactual of a female than in a male, and then we see, for instance, that marital status is one of those attributes that is used very often. And we removed gender from that. So let me take one step back. And so you have this data set, there is this disparity. We remove the sensitive attribute. There might be some proxy attributes, and that's indeed what we see here. And because the model will learn still predicts at a different rate for males and females. And we see that the explanation, if you would have changed the marital status, then my prediction would have been different. This is used more often if it's extended. It's used more often for females than for males. And for age, that's used more often for males than for females. And race is used more often for males and females, relationship, hours per week that they work. So these are, and some of those are valid reasons, and the hours per week that you work. If you work more hours, it's logical that you earn more, but marital status is probably just a proxy. And that's also what we observe, and there are some, this is a coded attribute, there are some codes and that much more often occur in the counterfactuals for the females than for the males. And it's marital status 2, I'm not entirely certain what it was, but one was single female and the other one was widow, and that was gendered. So this is basically the same. Another example where it proved to be useful to analyze the data set, and this is the student performance data set, and this has to do with this. So we have students and we have their results in high school, and now we want to predict how they will perform at the university, whether they will pass an entrance test, for instance. And if we learn a model in which we do not use the sensitive attribute in this case is gender, then we observe that we see a difference of 11% between having the positive label or getting predicted and that you will pass the test between females and males. In the original data set, there is a 0% difference, but if we look at we remove the sensitive attribute, and then all of a sudden we observe an 11% difference. So this is problematic. And where does it come from? And because if we train with the sensitive attribute, the difference is only 4%. So actually it's correcting, and we're only trying to optimize for accuracy. And if we remove the attributes and that correlate with the sensitive attribute and the sensitive attribute, and then we will also get a lower difference between males and females. And so this is on original data, almost no difference between people that are passing the exam or not. If we force our algorithm to make predictions not using the sensitive attribute, and then actually the error increases, there is a higher difference. And so if we should use gender in order to make a better classifier. Now, why is that? And so there we could again study the counterfactuals. And so again, we look at females that are predicted to have the negative label, and we see which of the attributes should change in order to get the positive label. And then we see that school is standing out tremendously. So the attribute which school someone went to is actually very, very important in predicting whether they will pass the exam or not. If we then look in more detail and we do the same analysis, but now at attribute value level, then we see that there are two schools in this data set, GP and MS. I don't know exactly what it stands for. And here you see the percentage of boys that go to this GP school versus the MS school. And so the blue bars add up to 1, the red bars add up to 1. And so you see that one school is, there are more boys than girls. In the other school, there are more girls than boys. And it turns out, if you look at the score that people get in these two schools, GP turns out to be the better school, because the grades that people are getting is higher if you went to this first school and if you went to the other school, and the grades are lower. But inside both of the schools, actually girls are outperforming the boys. It's a small margin. It's not tremendously, but they're doing slightly better. This is a large data set, and so the difference is statistically significant. So what happens if we learn a model and we do not allow the algorithm to use the gender of a person? then it will use the predictive attribute, namely the school that someone went to. Well, it's always using the school that someone went to, but if the algorithm is not allowed to use gender, it cannot correct for the fact that inside each of the schools, the girls are actually doing better. And because of this, we actually see that the difference between the two groups becomes larger. And that's done. Also the explanation there. And then, based on this information, then we can start deciding which action we should take. When we make this prediction, for instance, for the university, who will we accept, how we will rank students if we have a limited amount of students that we can accept? Will we use gender or not? And paradoxically here, if we do not use gender, actually one group will be worse off, and the females, because more errors will be made. And in the other situation, it will be more equal. And then it's a policy decision whether or not to use gender. So to summarize, 3 main conclusions. And the first conclusion, looking at the data alone, we cannot know what exactly happened and led to this data, to disparity that we observe in the data. Second observation, it's really important to know it, because if we use the wrong assumptions, then actually we will do the wrong mitigation. We may actually make the situation even worse. Third conclusion, directly optimizing for the fairness criterion is not a good idea, because then we get all these kind of side effects, and we will that we are actually punishing one group in order to make errors equal. And then the last message, I think explanations are one of the key components in order to mitigate the situation somewhat, and to understand what is happening, why models are making mistakes or different predictions for different groups. And based on this information, we can take the right decisions how to mitigate. Thank you.
We have time for taking 1 or 2 questions. Yeah. We have some time just to take 1 or 2 questions. Yes.
I can say.
Okay, good.
Just one question on the table you presented just before this slide on the 2 kind of school and performance of, for instance,
Next one.
slide.
Yes.
This one? Yeah.
What is the margin of confidence of this level? Because here the difference is not so huge, and therefore here maybe the margin of confidence may overlap the gap we are seeing on the table.
I don't know by heart. No. Yeah. I need to look it up, but I can. The only thing I can say is that the number of students in these data sets is quite large. And so the difference that we see here of which is like almost a point on average. Yeah, well, it's not very scientific, but it's probably significant. But I will do the statistics. Yeah.
An adult, there is the race also. What we can do if we have more than one sensitive?
Yeah, so that's a good question, and the way it's very often solved is, okay, we just take the Cartesian product of the groups, and then we look at individually, or we look at the 2 sensitive attributes separately, and we do the same exercise for the 2 separately. But if you do for the 2 separately, then you run the risk that there are combinations that are discriminated. Let's say that white men and black women are being discriminated. Then if you only look at the gender or only look at the ethnicity, you will not observe this behavior. So that's the danger if you treat them independently, and if you have an algorithm that tries to optimize for those independently. Yeah. So it's important to look at the combinations of the groups.
Thank you. One last question.
I had a question about your third conclusion, this zero-sum game, basically, that you're saying, right? You're saying if you optimize for fairness, at some point you're going to discriminate the group that you that was not discriminated first, right? So leading to a zero-sum game. So is that always true, or is it? I think it's taking a bit the perspective of a static world where your data are just as they are, and there's no opportunities to get more data. But would it be maybe a solution to go away from the zero-sum game by just saying, okay, let's collect more data, and maybe you collect them in a way that we can actually benefit for both groups, right? So in that case, maybe you can optimize for fairness and not penalize the non-protected group. Would that make sense?
Yeah, it definitely makes sense. And I think it's a very, very valid remark. For instance, in insurance, if you see that there are differences in risk between males and females, and you're no longer allowed to use the gender of a person, like one solution could be, of course, to gather more information, like the number of kilometers that someone is driving, or maybe get some more statistics on how many accidents they had in the past, or how their driving behavior is. Yeah. Yes. Yeah.
Thank you very much. Thank you, Todd. Thank you very much. And now, so we let the floor for Isabelle Valera. The floor is yours.
Can I use the clip? Hi, good morning, and thank you for inviting me to be here. So, in today's talk, I'm gonna try to revisit some of the work I have done in fairness and some of the learnings I have gotten. And I'm going to try to summarize also my current attempt to try to involve other stakeholders from other disciplines more actively in the design of AI algorithms. So I'm a machine learner, so I'm going to take a perspective from the development of algorithms for decision making and more generally AI systems. So let me start by, I usually get very frustrated when people don't define what they mean. So let me simply restrict my context of today to say, well, when I talk about an AI algorithm, I basically mean a computer program that learns from historical or training data how to automate a task. So every time I talk about AI, model, algorithm, that's what I actually mean, how to automate a task from some data. And when I talk about discrimination, which is basically what we refer most of the time in fairness in machine learning, I'm basically going to assume that we are somehow wrongfully imposing a disadvantage on a subpopulation, which is not justified, right? So you have seen a lot of this news when we started, I think some people started earlier, like Toon. Some people like me, we started around 2014 or so working on these topics, and especially in the context of algorithmic decision making. And we saw a lot of cases in the news that algorithms can discriminate. And as we are moving to the generative AI era, this has not changed. It has only been shifted. And for example, we talk about, there is this Bloomberg article that says humans are biased, algorithms are even more, right? So today I'm actually going to talk a lot about the role of algorithms and amplification and where, in my opinion, these things happen. So let me start with my simple example, which is algorithmic decision making. Let me start by pointing out that an algorithm only sees an individual as a set of features, right? So there is no side information. There's just a set of features, how they have been collected, how noisy they are. That is everything that the algorithm is going to see. And something that we know is that when we take the perspective of the decision maker, we can derive an optimal decision policy by simply saying, okay, I'm going to make a deterministic decision that says I'm going to make a positive decision if the probability of a positive outcome is greater than a cost of this decision to be bad somehow, right? And just to make this very clear, this probability that we have here is the underlying true probability of someone, for example, to repay a loan. And I don't think any of us have a label here in our forehead saying my probability of repaying the loan as for today is 70%. So what we actually do most of the times in machine learning or in algorithmic decision making is that we train what we have been calling a classifier that basically predicts or estimates this probability and then use our model as a replacement of the true probability. And this is how we have been automating our decisions. We have seen that this has some problems, fairness problems, and a lot of the effort or the blames go very often to the data. No, it's the data that is biased. Maybe we have selective biases, and it's actually true. There is a lot of reasoning or a lot of sources of unfairness in the data. But I think from a point of view of developing methods, I think we can go a bit beyond. And actually, where I believe we put very little effort is at assessing our assumptions and what I call the societal cost of wrong assumptions and feedback loops, so which very often will explain the amplification effect. So I'm not saying that these 4 initial points related to data are not important. I'm simply saying that from a developer point of view, it's kind of washing away the responsibility. It's the data. No, it's the data and also the decisions that you make for your models. And I will also argue that very often in our mathematical or algorithmic formulations, we have transferred this, what I call owner-centered or decision-maker-centered point of view, where we did this mapping from decision-making, optimal decision to prediction and then decision, a bit too automatically. And I think this owner-centered has some cons. And I'm going to show you basically 3 examples of assumptions that we have kind of interiorized and say, okay, this is ground truth assumption, I'm going to believe it, and what is the potential societal impact that they may have and how we can address them, even though it's going to be challenging, as you are going to see. So let's start with assumption 1, decisions as predictions. Basically, everything I said before is that the problem of algorithmic decision making, we have said it's a matter of predicting the probability of an outcome for an individual, and then I do everything according to the optimal decision making policy if I knew this true probability. But when we train a classifier or any predictive model, mostly any predictive model, there are some assumptions on the data that we are making and that very rarely actually are true. The first one is that the data is a representative sample of the population where we are going to apply the algorithm, and there is, for example, no selective biases. Bias selection, as Toon was talking, I call it here selective labels because, for example, in the context of lending or in the context of insurance, you only get to see whether someone will repay a credit or will have an accident if you actually grant them the insurance or the credit. So there is already a pre-step that says who I'm going to get to observe and who I'm not going to get to observe. And usually this decision is not made at random because that would be not very efficient and also probably not very morally acceptable. But this imposes a selection bias that directly violates our IID assumption. So what actually happened, and I'm going to go very much into the math, is that if we take decisions sequentially over time, so every round, every day, there is a new population of applicants for the credit or for the insurance, and we make decisions, what actually may happen when we do this translation is that we may end up, this is what I call prediction-based policies, in policies that are suboptimal in terms of utility for the decision maker, but also have a very big amplification effect in terms of unfairness. These black lines are simply the optimal solution that you could reach if you would have full information. So something that we have actually shown is that if we add a bit of stochasticity in our decisions, so instead of thresholding imperfect predictors, we use our uncertainty to add a bit of randomization to the process, we would be able to discover or get more information about those populations that maybe we are more uncertain. And we are not gonna only be fairer in the sense that we can make fairer decisions, but we might end up in better solutions also for the decision maker, because you can reach a higher profit, for example, right? So with this example, and I have not imposed any fairness constraint here, everything I'm saying is that by just minding your technical assumptions, you might get systems that work better for everybody. So it was not only the data, it was also the assumptions that we were making here. The problem that you encounter in these cases is that, first of all, as Toon was saying, given a fixed data set, it's very difficult to know whether you are suffering from such a bias. So I think we need to collect not only the data, but also under which probability, for example, this data has been collected. And there has been also a bit of discussion about stochastic decision making, about their moral concerns, right? Because you are saying that to some extent, for at least some individuals, I'm gonna be sampling the decision. So I would argue that I'm not gonna enter too much here today, but I would like to point out that when I talk about the stochastic policies, doesn't mean I'm gonna make decisions at random. Everything I mean is that I'm gonna use the uncertainty in my favor to improve for fairness, because we always believe that the label is kind of ground truth. They repaid or they didn't repay. Well, under different circumstances, the same individual could have been repaid, could have not repaid, or in the other way around. The same with insurance. A car accident is not dependent only on the individual in the car. It has a whole environment around that we have not control on, right? So this is something we are going to discuss a bit later, but it is important for me to start the discussion on the role of stochasticity, as well as of thinking of the effects or the measurements of course, profitability of a decision-making process, but also fairness in the short, in the medium, and also in the long-term processes. So I think when we look at this prediction point of view, we are very static in time, but we also need to kind of forecast what will happen in the future. Problem is that, of course, making explicit assumptions unverifiable, so the verifiability is the problem, is not an easy move. And that becomes even more challenging in much more broader scenarios. So if we go to the generative AI era, right? Here I have simply one stable diffusion. So this is just a generative model that, given some prompt, for example, color photograph of an engineer, generates these images. Just for your information, I'm an engineer. I don't feel quite represented here. We look, for example, at the global gap, global gender gap in 2023 in terms of STEM professions, and we can see that there is a gap, but there is roughly 30% of women that work in the technical side. I would say this is a clear amplification case, and this is just a subset, but it has been systematically being proved. The problem I'm trying to point out is that it's very hard here to say what is our reference point, right? Even in the decision making was already difficult, but now when we go to this generative AI, it becomes even harder. Is it this kind of statistics, reports, our reference point, or where do we go? I'm gonna give you questions, but no solutions today. I'm happy to evolve in solutions. So the second assumption I'm gonna challenge today is that we very often think of fairness in terms of binary decisions and binary outcomes. I grant the insurance, I grant the loan, someone repays or not, or they have an accident or not. And that is quite limiting, because I would say that when I went to the bank and I asked for my mortgage, it was not only whether they would grant me or not the loan, but there were a lot of terms that were decided: amount, interest rate, duration, collaterals, a whole world. And I would argue that I would have liked to have control on these decisions. I didn't. If I would have put my interest rate, it wouldn't be the one that I got, right? So something I'm actually arguing for is that we measure fairness in terms of this relationship between I grant you the loan and you repay, but there are some potential other decisions on the path for what I call treatment decisions. Here, it could be the loan terms that actually are also partially under the control of the decision maker and also may have an influence on the final outcome. Because it's not the same for me if in order to repay my mortgage every month, I commit 30% of my salary, than 10%, than 50%, right? And of course the banks have some control ratio, but it's also not the same a 30% percentage of a 5,000 euro salary than to a 1,000 euro salary, right? So one needs to kind of be careful about that. So what I've been arguing for is that we actually need to be a bit more transparent on the data generation process and which decisions are being happening in the process. So here what we did was to say, well, let's imagine in the lending case that we have the sensitive information of the individual, we have the covariates that they inform the bank to apply, and then based on that, the bank and the bank makes some treatment decisions. They agree on loan terms, and if everything goes well, I get offered the loan and I accept it. Eventually, I get to see whether I repay or not, right? So what I would argue is that this mechanism, this treatment, is under the control of the bank, and we should assess for its fairness and also for its downstream effect. So this is just a causal graph summarizing the pipeline that I had before in a structured way. And what we observe is that in this German data set is that when we were looking at treatments like amount of the loan or duration, we could see that it felt that males were getting a more advantageous term than females in some cases, but we also, or more risky, I would argue, because what we actually observe is that some of the males, if they would have gotten a more conservative treatment, other terms, so a bit less amount, they would have been able to repay their loan while they defaulted in reality. So all this is based on causal counterfactual estimation. I'm not going to go into the details of that because it would take me another hour, I guess. But everything I'm trying to say is that decisions very rarely are binary. And there are a lot of sources where biases can pass. And sometimes we oversimplify. I think Toon had a few examples where it might be that it might look like we are discriminating against, for example, women, but actually it may happen in the opposite direction. So I would then say that actually causal reasoning doesn't need to be fully causal inference, can be helpful to have structured ways of keeping track of the different decisions when they happen, kind of in a sequential manner, and reason about what sources of unfairness or of biases we might consider fair or unfair. But it also triggers a lot of problems, like how do we do causal inference or discovery under realistic assumptions. My group, we have been working a lot on removing some of the inference assumptions. I think verifiability, which is my first assumption, is our main challenge. But I'm not giving up, and we are going to try. But that's not the only challenge. If I go back to the AI, this is a simple AI generative AI life cycle represented in a diagram. That looks way more complex than the diagram I had for the decision making, right? So if I need to keep track of all the decisions made in this process, assess for their fairness, and if necessary, correct for that, the process is not straightforward. So I think one challenge that we need to address is how do we keep track of all of them, or at least have a transparent representation of when these decisions are happening. So just to finalize with my third example, I'm actually quite rewriting myself, because very often we have formalized fairness as a constraint to performance. Actually, this is for one of my papers, kind of maximize performance subject to unfairness. And we have kind of interiorized that there exists a trade-off. And now we need to decide whether you are profitable or you are fair, and you always need to compromise, right? And to some extent, that's true. But I'm going to show you that maybe it's not as bad as it looks like. But it also comes to the assumptions that we make. So already we have seen that there might be a mismatch between our fairness, accuracy metrics and the reality under some assumptions. Toon was actually giving some examples, and these examples, for example, include counterfactual fairness analysis, where you say, okay, my label is informative about the quantity that I'm interested, but maybe it's not really what I want to measure, because what I want to measure, for example, the knowledge of my students is unmeasurable, and everything that I get is their performance in the exam. Right? But I would say I observe that very often, that students that are very used to the German system, they tend to perform better than those students that for the first year they arrive to Germany and they need to deal with a new whole system, with a new whole language, and then it takes them a bit of time to recover. So if I use as my proxy the first year grade, the poor foreign students usually will say, well, they are very much worse than the others, right? So we have already seen that these trade-offs sometimes are not a reality, but they are just an artifact of how we measure fairness. But I would actually also argue that it is an artifact of our family of decision-making class of policies, policy class, and also how we address the problem. So what I'm actually exploring is that what if we move away from seeing fairness as a constraint to performance or accuracy, and we start looking at it as an objective maybe from society, from policymakers, from regulators, right? And we adopt a more multi-objective perspective where I try to find the family of policies, because now there is not going to be only one optimal policy, there is going to be a bunch of them that jointly maximizes the utility, for example, for the owner, and the utility for the regulator, which can be some sort of fairness, right? If I look at that, first of all, here there is a plot with accuracy and equality of opportunity, so thank you, Arthur and Toon, for introducing these notions. The first thing that I observe is that for deterministic policies, which are these solid lines, right? If I want to achieve fairness in terms of equality of opportunity and accuracy, the first thing I need to do is to have a different policy for males and females. I need to have different thresholds. However, at the moment I allow for adding a bit of stochasticity to my decision-making policy, so I'm not making decisions based just on my prediction. I'm gonna compute a probability of granting a positive decision. I can get much better fairness values for the same amount of accuracy. Right? So here, if we see this is my accuracy, we can see that the unfairness is much lower if I add some stochasticity. That is simply because, as I said before, labels are not deterministic function of what I observe. There is uncertainty. And basically, a stochastic decision-making policy can leverage this uncertainty to balance for fairness without, on average, losing predictive power. And you can already see that with one single policy, in some cases, we might be getting quite close to the accuracy of other systems, of the group-specific based policies. Going even further, I would say that right now we are looking at accuracy and equality of opportunity, but actually not always the quality of a decision for the owner and for the decision maker and for the decision subjects need to live in the same space, right? So maybe for the bank that was granting me the loan, they live in whether how much interest they are gonna get out of my loan. For me, it was important to guarantee my family some sort of stability in the form of a house and stop moving from one apartment to another, right? So taking the notions from more justice-based fairness notions, what we can actually observe, I'm not sure whether the yellow is very visible, is that if we move directly to energy utility rather than accuracy, which is ultimately what you are interested in, and we measure fairness in terms of the disparities between the utility of consumers across groups, we actually can get much better benefits from stochastic policies compared to deterministic ones. What do I mean by much better? Basically, you get better trade-offs because you always want to go into that direction, right? Low unfairness and high utility, and you can observe two things. First of all, that we can get better trade-offs, so our trade-offs don't need to be as restrictive as before, and that sometimes you don't need group-specific policies to actually be fair and accurate at the same time. So what I'm trying to argue for is for more transparent trade-offs. So in different asking different stakeholders to tell us what they care about. So what are the risks or the benefits that they see in an algorithm? And this aligns very much with the EU Act, where if you are in this range of limited or high risk, you have a bit of flexibility. So I would argue for asking stakeholders to introduce their functions, the utility, benefits, or risk functions, and try to have more transparent trade-offs between them such that they can do jointly an informed decision. How far I will reach, I'm not sure. But basically, to summarize, I have shown you 3 consequences of doing this direct mapping from optimal owner decision-making policy when we incorporate fairness. I have shown you that there are quite some challenges that appear from moving away from that, but I still believe that adopting what I call a more society-aware approach where we involve different relevant stakeholders can be is still worth, because first of all, it allows us to consider the benefits and risk for all stakeholders. It will allow stakeholders to, without having very much expertise in AI, have a more efficient oversight. So moving away from normative processes more to procedural fairness processes, and ultimately, hopefully, having a more informed discussion and agreement on what we want out of these technologies. I don't enter in what is a good trade-off. I just want to make the trade-off more transparent such that people can make hopefully a more informed decision. And with that, I have concluded my talk. I'm not sure how I'm doing with time, but thank you very much.
Thank you very much. You are doing perfectly well. So we have 15 minutes for questions, so plenty of time, comments, questions, reaction. Yeah.
Okay, this is really interesting, and I appreciate how you revealed how like the classical trade-off picture and really framing assumptions that are made by large majority of papers gets reconfigured once you recognize the inherent stochasticity of the data points from which learning takes place. So I'm gonna push you even further. The problems we are observing, this was extremely clear in the previous presentation, is so difficult because it's not like we are dealing with a fairness constraint, like a single one. I mean, even when the mathematical one is just one, when we start analyzing the effects in the way the previous speaker did, it became clear that we are trying, if we try to do our work well, we're trying to minimize norm violation for multiple norms simultaneously, and these norms conflict. Now, what if we also consider that all of these norms have, at the very least, uncertainty? Some people will say they're completely subjective, so why should we take them seriously? As a moral philosopher, I don't take that line. But at the very least, we can say, well, we are uncertain, you know? People disagree about these things, so how do you think something could be gained if we also try to model the uncertainty about the moral requirements that we actually trying to fulfill?
That's a quite interesting and difficult question. I think maybe a simplistic approach, because I'm not sure I grasp all the depth in the question, is that is, I mean, I think this is why I argue for transparency, right? So if to some extent here I saw only two objectives, it's simply for visualization purposes. You can have as many objectives as you like. And I'm not saying, so far I'm not even optimizing for them. I'm simply showing, okay, what is, given your decision-making policy class, what are achievable trade-offs that are optimal for them, right? And you can do that in 2, 3, 100 objectives, right? Later on, exploring them is a different question that I'm also dealing in a separate, very statistical research. But I would say that if we would manage to some extent measure or get proxy measurements for the different moral values or definitions, right? You could try to represent them together. And I think sometimes when you get to visualize some of them or compare them or put them together on the same pipeline, at least people can start having a more informed discussion of what are really these objectives, whether maybe two of them that might look very far away, they are somehow collapsing to the same subset of solutions, because sometimes this happens, right? Sometimes it might be that a single policy it's good in two objectives that look arbitrarily bad. Maybe it's not perfect in both. But at the same time, when you talk about uncertainty, all these data-driven approaches, I haven't shown here much of the variance because it was already crowded, right? You can also measure to some extent uncertainty or variance into your decision-making process, and which comes also from the data finite sample that you get, right? So I think my argument would be, if you have more objectives, let's try to put them together. Let's try to see whether these trade-offs exist. Let's try to also measure uncertainty about them. And let's start the discussion a bit from there. But that is, of course, a very computer scientist-centric approach. I think it's an approach that could involve AI practitioners to talk with other practitioners. But yeah, I'm still exploring.
Thank you. There was another question, yeah.
Yes, thank you for the really interesting talk. So I have multiple questions, but I'll stick to one, so maybe I can ask the second one later to you. So you talked about causality, which I found really interesting with causal discovery, which seems like a really complex topic. So I'll just say like a macro view maybe of this, but we sometimes hear that causality is nice, but it's pretty assumption heavy. And maybe it's not necessary because we only have to correct for statistical association. So I'm just curious to hear about maybe your view on this.
I think my view as of today is that there is a lot of aspects in causality. First of all, there is the graphical representation, which is the causal graph. Sometimes the causal graph, at least at a high level of granularity, like here I have put all covariates together, all sensitive information together, and all treatment together. So these are clearly multidimensional variables. This order or this graph, at least the causal ordering, which is what comes first, right, can be already collected from the way in which the data is generated, right? And in that case, for example, we don't need causal discovery tools. So there are other cases where people can phrase their assumptions as causal models, and I think usually I work with at least having some partial knowledge on the causal graph, and that already helps the reasoning. As for the inference part, which is doing bias correction, I think there are different levels. The word in which machine learning usually lives is the observational level, right? You observe the joint distribution of all these, and then you argue in terms of conditional independences. I think causality allows you to go one step beyond, because you assume which conditional probabilities are aligned with the data generation process, and therefore reason about that, and do the right statistical corrections. Of course, for the fairness, it would be amazing to have it at the individual level, which is the counterfactual world. I've done plenty of work there, but I always encounter the same wall. How do I verify? Right? So I think to some extent I can verify the interventional one, so the adjustment part at the subpopulation level, with some interventional data, and I think something between population and individual is subpopulation, and this is what I'm arguing as of today, because I think there are realistic assumptions we can make there, but it's definitely challenging. I would say statistical approaches are a bit limited, too limited for my taste. Counterfactual are, for my taste, probably too hypothetical as of today, but why not to find a middle point where we can get the best out of the two worlds, and this is what I'm trying. How successful it will be, we will see.
Thank you a lot.
Thank you.
Hi, thank you very much for the presentation. I had a more general question about the importance of alignments for artificial intelligence, whether it is the machine learning definition or nowadays more the generative AI definition of AI. My question would be, would we even be able to measure the impacts on fairness or unfairness of the alignment error when it comes down to training a model and formulating the problem to an artificial intelligence, whatever the definition of AI is in this case?
That's actually a very good question. And that comes back to my beginning of my presentation. Very often I encounter that many of these terms are highly abused and very ill-defined, right? So I think if we talk about alignment in the way that is happening, for example, in the terms of personalization of large language models, where you take the basic model and then you do some refinement in the probability distribution, the output probability distribution to personalize for individual, I think like with any other feedback loop, because this is a clear feedback loop. You get an output, you get feedback, and then you refine. That brings me back to the short, medium, long terms, right? And how much assumptions we can do on the distributional shifts and which stationary, if any, state we are gonna reach. So I would say I'm not the biggest fan, and this is my personal opinion now, the biggest fan of hardcore personalization or optimizing for every individual, in the sense that you have a huge feedback loop that can end up in very undesired states. So I would say, for the sake of transparency, I think we need to find a good balance between which level of personalization and when to perform, and such that ultimately you can forecast where you are going to converge in terms of this alignment, and whether you are going to reach a state that is socially acceptable. And of course, socially acceptable will change over time, right? But this is why we need transparency, because our morals or our social agreements seem to be changing over time. And everything I aim to contribute is to make things more transparent, such that we make more informed decisions, or at least more collective decisions. For the rest, we will see.
Thank you very much.
Thank you. We have time for one last question before the lunchtime that I'm sure you're all looking for. No? Oh, in this case, thank you very much. So as I said, so now it's time for lunch, so getting some energy for the next round. So we have almost 1 hour just for the lunch. So in 1 hour we'll resume the presentation, and yeah, enjoy.